going to spend more time on this tone, please.
All right. Thank you. Thank you. Okay. Good. Is this amplification on? Yes. Great. Good. So that's right. Those seminars that we had when you were out there, one of the points of the seminar is everyone could speak for up to 2 minutes on whatever they wanted to, but that's out for this one. So what I like to talk about is the natural mathematics that is common both to investment theory and to information theory. So the emphasis will be on the investment theory part of it. And necessarily I'll go through an amount of known material and so on, plus some new material on acceleration of investments and some open problems that will bring us up to date and beyond. Now, so the emphasis here will be on maximizing the growth rate of investment. Makes sense, doesn't it? You want to put your money in such a way each day that your money goes to infinity as fast as possible. And I think there's a satisfactory theory for it. It doesn't, but the strategy achieving the goal is controversial. It has to do with maximizing the expected logarithm of the wealth, at least in those cases where you know the underlying distribution. Now, the problem with log wealth is it suggests a log utility. And maybe for that reason, or maybe for other reasons, this is growth optimality has encountered a massive amount of resistance in financial mathematics. And so what I would like to do here, rather than make a pitch for growth optimality and its attendant way of achieving it, I'd like to reverse it and just say that the whole theory of growth optimality is a natural mathematical theory, and that the pieces fit together, and therefore for aesthetic reasons, which is always a dangerous reason, it is a good theory. You know, physicists are always coming up with aesthetically nice principles like F equals ma and so on, and then getting nice consequences like elliptical orbits. And they like to justify physics on the basis of the aesthetic appeal of the mathematics. In fact, people have pointed out, isn't it interesting how nice mathematically our physical world is? Well, in physics, you try to predict properties in physical events that you can then test experimentally and thus validate the theory. Well, in a mathematical theory, there are no events to really predict here in growth optimality, but maybe you can predict other properties of it, and therefore validate the theory, at least aesthetically, that way. Here's an example. You have the real numbers, you have the nth degree polynomial, and you have a number of roots. It's no larger than n, but could be very small, maybe none. But if you go to the complex numbers, all of a sudden every nth degree polynomial has precisely n roots. So you feel that the complex numbers are a natural extension of the reals for that reason. All right, so similarly, pi is fundamental because it's the answer to several different questions. One in geometry, circumference to diameter. One in number theory. I guess Euler proved this open question after it had been open for many years. And then it comes up in the central limit theorem, yet a different kind of question. So we'll look at many properties of growth optimal portfolios. And there are no moving parts, it's just growth optimal. And we hope that it predicts other properties. And I'll try to mention along the way some of the new results. All right. I'll do a setup, a slide on the mean variance theory, and then some properties of growth optimality, stability, expected ratio optimality, competitive optimality in the short run, the fact that the growth optimal portfolio acts as a numeraire such that any other wealth with respect to it is a martingale, or more precisely a super martingale, and then a probability 1 behavior of it. Then I'll throw away all statistical assumptions and look to find a portfolio algorithm based solely on the past that doesn't involve modeling, doesn't involve learning, but involves jockeying for position so that no matter what the market does, including crashing or going through the roof, that you do as well, Sn hat, as the best constant rebalance portfolio in hindsight, up to first order in the exponent, which means asymptotic negligibility of the cost of universality. This parallels in information theory the result that there exist universal data compression algorithms. For example, you know the Lempel-Ziv data compression algorithm. It takes any file, music, text, bit stream, and compresses it to its entropy limit in the limit as the length of the sequence goes to infinity. In short, it does as well as if you had known ahead of time what the underlying stochastic process was associated with that file. So similarly, we would like the same thing in the stock market to do as well as if we'd known ahead of time the empirical performance of the stocks, as if you could look ahead in the newspaper. And throughout, I'll be mentioning the relationship to counterpart theorems in information theory. All right, here's the setup. There are M stocks in general that we'll consider, and we'll suppose we know the joint distribution of those stocks. So X1 might be IBM, X2 Coca-Cola, and so on. And a typical value of X1 is 1.02 or 0.98, because these XIs aren't the prices of the stocks, but they're the price relatives, which are the ratio of the closing price of the stock to the opening price of the stock. So 1.02 corresponds to a 2% rise in the price of that stock that day. Now, a portfolio is nothing more than an allocation of the resources, which we normalize to 1, across the stocks. It's the proportion you invest in each stock. Generally, we will let these proportions be non-negative, meaning long-only investments. But if we let them, some of them be negative and some positive, they have a precise interpretation as short selling and buying on margin. By the way, buying on margin allows you to leverage and invest more in a stock by shorting cash, and short selling allows you to invest more in cash and less on the stock by shorting the stock. So short selling and margin are basically the same thing, except that if one of the investment opportunities is a risk-free asset, say cash, then going long on cash is shorting the stock. Going short on cash is going long on the stock. Okay, or buying it on margin. Okay, so there's nothing to investment theory than choosing that portfolio which maximizes the wealth at the end of the day. So if you start with $1, you'll end up with a random variable S at the end of the day, which is B transpose X. So you simply choose the largest random variable. But of course, you don't know what that one is. By the way, gambling is simply the exchange of one random variable for another. Your random variable going in is $1, your random variable coming out is whatever happens when you gamble. So the question is, how do you compare these random variables indexed by B? You want a good basis for action, choosing your portfolio B. So the mean variance theory says, let's see, a good thing to do in life is to maximize your expected value. So if you maximize the expected return from your investment B in the stock market, where you know the distribution F, you maximize the expected value, and you find out that's just putting all of your money in the stock with the highest expected value. That's not diversified or anything. It has a high degree of risk. So you put in by hand a correction term to keep you from doing something clearly stupid, and you then decide to include the variance term. And then now you wish to maximize the mean subject to a variance constraint. So here the portfolios indexed by B give you mean variance payoffs on this, and then here's cash, and you get what's called the efficient frontier. These are points that are undominated in the mean variance plane. So that would be a good way to invest. The problem is that there's a conflict between mean variance theory and growth optimality. The portfolio which maximizes the growth rate of wealth, which we're yet to get to, can be shown to give you a mean variance pair that need not be on the efficient frontier. It may be dominated in mean and dominated in variance. So, what to do? Okay, the general setup is this. If you have repeated investment opportunities, a stochastic process market, then you need to know on day I how much to invest in stock J based on the past. And you demand that you never invest more than you have. It's self-financing. Okay? And so now you're left with a random, Sn is still a random variable, but now it's the amount of money you have at time n. Here's typically what you would have to invest in. This is an old slide. Over, let's see, a period of about 20 years of two low-cap stocks called Kinark and Iroquois. Kinark, I don't really care which one Kinark is, but here it is. At the end of 20 years, it's gone up by a factor of 4, and Iroquois has gone up by a factor of 8. By the way, looking ahead to universal portfolio, notice that if we rebalance, say, half-half in Iroquois and Kinark, we go up, say, by a factor of 52. It's one of these curves. And in fact, this point, which is 70-something, is achieved by a constant rebalancing of 52-48. So if you'd known ahead of time how to rebalance, you could have achieved this upper point on the envelope of all these curves indexed by your rebalancing factor B. And in fact, universal portfolio is one that tries to track the maximum of this envelope to within the best factor possible for any pair of sequences of stock price relatives. All right. First, so to begin with, let's just look at growth optimality for an IID market. Independent, identically distributed, you know the distribution. The wealth at time n is the product of the wealth factors at time I, and the product is e to the sum of the logs, dividing by n and multiplying by n. You see that this quantity here converges with probability 1, because it's the sum of IID random variables, to its expected value. Plus, and there's some small random amount of change which is asymptotically negligible in the limit. It's the law of large numbers, but this is taking place in the exponent, and this expected value should deserve a name. We'll call it the growth rate, which is the expected value of the logarithm, and the maximum value over all portfolios, W star, and we believe then that the wealth will go to infinity at rate W star. So people will recognize this, that now the relevant theory for sums of random variables is to maximize the expected value of the terms in the sum, and that'll give you the best behavior of the random sum. Well, for products of random variables, the relevant thing is to maximize the expected log of the terms in the sum and the exponent. That will give you the highest exponent, and the resulting fact will be the law of large numbers for products, which is the geometric mean. In any way, so it's the geometric mean rather than the arithmetic mean, which is appropriate for compounding assets. Assets like your wealth in the stock market or the number of rabbits in Fibonacci's zoo or whatever. Here's a quick example of how you make money out of nothing. So, because that's essentially what you want to do. With data compression, you want to compress it to the minimum, even though you don't know anything. In the stock market, you want to make money, even though the stocks themselves behave in a boring way. All right, here are two stocks. X has two stocks in the component. The first component is 1, that's cash only. The second component is 2 or a half. The stock either doubles or decreases by a factor of 2. And these are with probability half-half. If you maximize the expected log, that is, if you find a growth rate, you find you should rebalance half-half each time. And even though neither stock goes anywhere, cash stays constant at 1. And in the hot stock case, the 2s and the halves cancel out because they each occur roughly half the time. Each stock goes nowhere. When you look at it here, you find out you're making 6% per investment period, essentially with probability 1. Here it is, cash and the hot stock, and SN star is going up. So what's going on? Basically, you're living off the fluctuations in addition to getting the intrinsic value of those two stocks, which are essentially 1. Okay, first we'll characterize the optimal portfolio. So you want to maximize the growth rate of wealth. To do it, you take the partial derivatives of the expected log. You find they are this very nice form, expected ratio of xi over b transpose x, and taking into account the inequality constraints on your portfolio, you get the Kuhn-Tucker conditions for this. And the upshot is a portfolio is optimal, growth optimal if and only if this is true. And a nice consequence is you could show that if the expected log ratio of someone else's wealth to the log optimal wealth S star is less than or equal to 0, then the expected ratio is less than or equal to 1. So in short, S star is a maximal element with respect to expected log criterion and an expected ratio criterion. Some more properties. WBF is concave in B and linear in F. So when you try to maximize it over B, there's a unique maximum of a concave function over a convex set. And this leads us down to this question here at the bottom. Let's see. Here's an open question. I'd hoped to resolve it, but I played around with it a few months ago and then just a week ago preparing, and I can't prove it. WB is a function of the portfolio B, and of course, the underlying distribution F. Now, I just wonder, is this a transform? What do I mean? Does W of B uniquely specify the underlying distribution F of X? Wouldn't that be nice? Notice, if instead of log B transpose X, I'd written e to the B transpose X, that is exponential instead of log, I'd have the moment generating function. And that, under mild conditions on the moments, uniquely specifies F. And if I'd written e to the I B transpose X, I'd have the characteristic function. And thus W and F would form a Fourier transform pair. And now it is uniquely recoverable. So there's some good chance that this is true. And I have an outline in which every step is nice on both sides of the gap.
But don't you need some conditional math?
Excuse me?
Don't you think you need some conditional math?
A composite?
The condition on F. Do you think it's true for any F?
Well, it turns out that there won't be any conditions on F. Generally, if you know a moment generating function, the moment shouldn't grow too fast or you can't recover the underlying distribution. But when you look at the derivatives of W of B at a given B, you get things like expected value of X over B transpose X. And that quantity is always bounded above by 1 over B or something. So there's all the moments are bounded by a constant. So it's very nice in terms of moment generating function. So you don't need to put any constraints on F in order to hope that this is true. All right. All right, so let's look at the second point. We now have characterized growth optimality as maximizing the expected log. So sometimes it's called log optimality. And now we see when do we, when is a portfolio log optimal? All right, here's one. Suppose you start 2/3 IBM, 1/3 Coca-Cola, and you know the distribution of how they'll go up and down. At the end of the day, it'll get a little lopsided. One might have outperformed the other. But there's an expected proportion you'll have at the end of the day. If the expected proportion at the end of the day is the same as the proportion at the beginning of the day, then that portfolio is log optimal, growth rate optimal. and conversely. So this follows from the Kuhn-Tucker conditions and the analysis on the previous slide. All right, now, much of the motivation I gave was for IID processes, but it goes through immediately for stochastic processes in which the stock vectors each day might be Markovian or have any joint distribution you wish. And the only condition is now that the portfolio you choose at time I maximizes the expected value of log B transpose xi given everything you know. So you just choose a conditionally log optimal distribution. Some people would say that's already what you're doing. If you know the distribution f of x, that must be everything you know, and now you're maximizing the expected value of log B transpose x. So it was conditionally optimal even when you thought you weren't conditioning on anything. You, in fact, were conditioning on the underlying distribution. Okay, now for some more very nice properties that shows you the naturalness of the mathematics. Let's look at the ratio of Sn plus 1, someone else's wealth causally generated, some investment scheme, with respect to Sn plus 1 star, the log optimal wealth, the one that uses the portfolio's conditionally expected log optimal. And we find that's a martingale. This ratio, at the end of the next day, has the same conditional expected value as the actual ratio today. So that makes it a non-negative super martingale, and therefore it has various properties. One thing is this ratio will converge with probability 1 to something. The something might be a random variable, but whatever it converges to, the expected value of it is less than or equal to 1. And not only that, because of that, there's a corollary. I think it's Kolmogorov's inequality that the soup of a super martingale exceeds t with probability at most 1 over t. That's the same as would happen in a casino. If you went into a fair casino, you expect to come out, or you go in with $1, you can come out with $1. But you gamble and gamble and gamble. Most people come out with less than $1. Some people with more than $1. If they come out at time n, the expected value of what they come out with, since it was a fair casino, will still be $1. But it's remarkable that when they come out and say, well, I've come out with $1.50, but one time during my gambling, I was ahead $1 million. It's remarkable that even that quantity, the most they have ever been ahead, the supremum of Sn over Sn star, the probability still satisfies the same inequality as it would for stopping at a given time n. That's nice. So by the way, when somebody says, you know, I'm broke right now, but I went in with $1 and at one time I had $1 million, they're wrong. Because the chance of that they ever have such a sad story to tell is less than 1 in a million. So either they're wrong or you should, this person's very lucky. Unfortunately, it's no prediction of luck in the future. And another nice property is that if xi is an ergodic stochastic process, which in some sense is the most general time-dependent process, includes ergodic Markov and so on in special cases, then not only will the wealth have a maximum expected log in the exponent, but that expected log will go to a constant, properly normalized, And in short, your wealth will go to infinity at rate W with probability 1. Or another way to say it is the nth root of your wealth goes to a constant with probability 1, which is e to the W star. Okay. All right, let's look at another aspect to see if this fits in with growth optimal theory. What if you have side information? Well, if you have side information for, suppose you want to describe a random variable x. Well, it takes h of x, the entropy, to describe. Somebody gives you side information y. Now it only takes you h of x given y bits to describe. That difference is the mutual information. The value of side information in description is mutual information. So if mutual information is 5 bits, then you can save 5 bits in your description. Well, for investment, we say, well, there's a growth rate of wealth associated with knowing nothing other than the distribution of x, and another growth rate of wealth in which we let our portfolio depend on side information y. Now let's suppose x and y have a certain joint distribution. Let delta of xy be the increase in the growth rate associated with the side information. By the way, side information never hurts. Well, it could hurt, it could be wrong, but on the average it can't hurt, because if it did, you could ignore it. And that's one of the allowed strategies for dealing with side information. So it can't hurt in the growth rate of wealth. And then there's a theorem that says, the increase in the growth rate of wealth is less than or equal to the mutual information. And it's with equality if and only if the stock market is essentially what's called a horse race market, in which each day only one stock survives and the others go to zero. Much as in a horse race where your ticket on the winning horse is worth something, and on the losing horses you could throw them away. Now actually some people collect those losing tickets and put them in a box so at the end of the year they can claim them as losses. But that's illegal. Okay, now for something that has nothing to do with growth rate. One of the breakthroughs in the early 70s was in stock option pricing. So we have, in the original work of Black and Scholes, cash, $1, or a stock, xi, that either goes up, u, or down, d, with probabilities p and q. All right, that's nice. Can you make money off this? Well, maybe you can, maybe you can't. We could analyze it. But an option was made available where you pay C units for this option that allows you at time n to buy the stock at price K. Well, that's great. So this option, if the stock's selling at greater than K, you pocket the difference. And if it's less, you throw away the option. You don't want to exercise it. So here's yet another random variable, xn minus k positive part. And the question is, how much should you pay for this option? So let's analyze it for n equals 1. Same analysis by backward induction works for n periods. And the idea of Black and Scholes was to replicate the option by buying and selling cash in the stock. So you don't need the option because you can get something, x minus k positive part, by a linear combination of cash and the stock. How much you need to invest in each to replicate this, that sum, is a good price for the option. Because now, you say, somebody wants to give you the option for more. I mean, charges. All right. Somebody wants to charge more for the option, or someone wants to charge less for the option. By this replication of this, you can then pocket the difference between the price they're offering for the option and this critical price that you've calculated here. There's an arbitrage opportunity. So this allows precise option pricing, which didn't exist before the Black-Scholes work. Okay, what does this have to do with growth optimality? Well, there's another way to look at this. You could look at it as there are actually three stocks, one, X, and the option, which you pay C units per unit of option. And now the real question is when does this option cause the growth rate of wealth of this triple to be higher than it would be of the double? When do you want that option, and what critical price? So the way you do it is you first just look at 1 and X, find a growth rate optimality and the optimal mixture for that, call that X star, then mix X star in with this third opportunity, do the necessary optimization, and evaluate the derivative at 0, which would tell you when you first want it. And when you're done, you end up with a critical price of expected value of X minus K positive part over X star, where X star is the growth optimal of cash in the stock alone. Well, that's nice, because this turns out to be precisely the same price as calculated by a no arbitrage synthetic argument on the previous slide. So the Black-Scholes option price, and this has become known over the last 20 years, the Black-Scholes option price is completely compatible with growth optimality. But growth optimality gives you something more. This formula doesn't come out of the no arbitrage theory, because for stocks taking on multiple values up and down, you can't synthesize the option. So this gives you a general way to price a stock even when you have an incomplete market. All right. Now, something more, asymptotic partition principle. If I have an ergodic process of like x1 through xn, it turns out that when I actually see what happens and what the probability of it is, its probability is going to be essentially 2 to the minus nh, where h is the entropy rate of that process. And there are only 2 to the nh things that will happen. So every ergodic process is nothing more than asymptotically a uniform distribution over some small subset, 2 to the nh in number, of subsequences. So a similar result holds for this market. Your money goes, whatever a market does, if it's an ergodic market, it will yield you the same wealth on that sequence. Here, whatever happens, you have the same probability of that sequence. All right? And if we specialize it to a horse race stock market, we get a nice fact that the growth rate of wealth plus the entropy rate of the process is equal to the log of the number of horses for if you have M for 1 fair odds. So there's a nice conservation law. So some of the tie-ins so far, before I go farther, is entropy rate and growth rate are similar, and one specializes to the other for a horse race market. Similarly, for an asymptotic equipartition property, here equipartition of probability, and here equal distribution of wealth. And similarly, when we get to universal data compression, there are similar results there. All right. What about competitive optimality? There's a question without any logs in it. You and I go into the market, invest today. And at the end of the day, we see who has the most money. So it's a game. I win a unit if I have more. You win a unit if you have more. 1-0 payoff. And it turns out if you solve that two-person zero-sum game and you allow a certain fair randomization so the other guy doesn't know what you're doing, he can know what portfolio B you're using, but you need some way to randomize so he doesn't know how much money you're investing. So you do a fair gamble, W, at the beginning. But the core of the solution is that you should invest in a portfolio B star that's log optimal. If you do, you've solved the two-person zero-sum game, and the probability you win the game is greater than or equal to a half. Why isn't it greater than a half? Well, because the other person could use the same strategy you're using, in which case you would tie. So there's yet another property having nothing to do with growth rate, which is consistent with growth rate optimality. All right, now I would like to do something in preparation for seeing what's been happening in the market the last 13 months. So now we have an arbitrary market sequence, the kind you see in the newspaper. Each of those stocks is a vector of, stock vectors is a vector of length m. You have m stocks, like 4,000 on the New York Stock Exchange, or 500 in the S&P 500, or just the S&P 500 index, in which you just have cash in one stock, okay? And now, I wonder what would have happened if I could have looked in the future over the last, say, 13 months or 20 years, and found the best constant rebalancing strategy B and used it. Well, then I would have made an amount of wealth SN star. That's the best result in hindsight. And the investor has to just choose some BI hat that's based on the past sequence. What should he do? Well, you can look at this. Well, before we look at this, here's Kinark and Iroquois, and here's who you would like to do as well as the maximum of this envelope. And looking at Kinark and Iroquois again, if you, B is the proportion you hold in Iroquois. If B is 0, then you get this factor of 4, that's buy and hold Kinark. And here you get a factor of 8, that's buy and hold Iroquois. And here's the 52%, 48% rebalancing that would have actually given you 75. Why? How can you do that? By continually rebalancing? Well, you're living off the fluctuations. I chose those two stocks because they had high degree of uncorrelatedness and high volatility. So you don't always get dramatic curves like this for the behavior of your wealth as a function of B. By the way, why do you get a bell-shaped curve? You always get a bell-shaped curve, no matter what two stock sequences you do, because W of B is concave, and S is e to the W of B. My favorite concave function is minus x squared. E to the minus x squared is Gaussian. So every time, whenever you do this empirically, you'll find Sn of B looks bell-shaped. All right, now, here's another felicity of the mathematics. The problem of coming up with a causal portfolio that does as well as Sn star to as good a factor as possible. In the worst possible case, is completely solvable. Rn star was called the minimax regret. It's the best factor you can achieve by choosing investor strategy B hat in the worst possible case. It's a min-max value, and it turns out min-max equals max-min. This is the value of the game. And that value of the game has a precise solution, which is really nice. V sub n is the sum of multinomial coefficients times 2 to the minus n times the entropy associated with these. And just to give you a feeling for this is the precise result, but you can look at the actual asymptotics of these to show that this factor is essentially square root of 1 over n. So we're getting the square root of n result that we are hoping for. And so a corollary is there exists a universal investment scheme that will come within a factor of square root of n of Sn star in any market whatsoever. The crash of 1929, the crash of 1987, 89, and perhaps even the current. And just to show you that it's an explicit strategy, and here it is. On day 1, you put half in each stock. On day 2, you see what happened in day 1 and do this calculation. And you see what happened on day 1 and do this calculation. And you bet these proportions on stocks 1 and 2. There's another way to look at it. You took 4/10 of your initial money with the intention of investing it all in stock 1 on day 1 and letting it stay in stock 1 on day 2. You took 1/10 of your initial money and with the intention of putting it all in stock 1 on day 1 and taking those proceeds and putting it all in stock 2 on day 2. And so you have 4 separate investors, each with their crazy plunging strategies, and you add up their wealth at the end of the day, and that's what Sn hat will be. And that strategy here is the one that I've spelled out in, from another point of view here, the same one. Okay? Before I show you what happens when you apply this to the real market, I would like to tell you one of the disappointments in investment is sometimes you know something's going to happen. The stock market's going to go up 2% tomorrow, and you have cash and you have your ability to invest in the market. So you put all your money in the market, it goes up 2%, you've won 2 pennies for your dollar. So what you would like is a way to amplify that. Well, there is a way to amplify it. You could buy on margin. You can essentially get 4 pennies for your dollar by buying 2 units of stock and minus 1 unit of cash. Similarly, if the market were going down, you could do it, amplify it. So amplification, and this is some of the new material, is if you know that the stock swings are not going to be more than, say, 10% a day, you know the stock vector will be close to the 111. It falls in this cone, then it should allow you to invest in the polar cone, the dual cone, the set of all vectors that form a positive inner product with your cone X alpha. That way it's self-financing. You have the broker who's not going to say, oh, I never should have let him do that because now he owes me money and I can't find him. So if you allow that, then you want to solve the same theory again. How do you optimally invest? Well, it turns out that if you look at this factor alpha that you assumed for the shape of the X alpha cone, the X alpha cone, you can find a linear transformation A such that A times the positive orthant equals X alpha, And A inverse times the positive orthant gives you B alpha. Those are polar cones. So basically, what one does is take the allowed investments and the stocks and put them in canonical form by using the linear transformation A and reduce it to a problem in the positive orthant that we've already solved. So the previous theory applies with this simple trick. But you get an amplification factor, which is tremendous. In any case, when you apply that to the alpha cone, you solve for the minimax regret and you get this simple formula. And the formula now involves rounding off k over n to the alpha bar interval rather than leaving it unrounded off. And so it's the same, essentially the same theory or the same appears to be the same result. All right, now let's have some fun. This is recent behavior. I think I quit this calculation on Wednesday of last week, October 14th, if that's Wednesday, I said. So this is through Wednesday. And backed it up all the way to September 28th of the previous year, not this year. So it's 13 months. And look, it was already bad. You know, like this frog of the witch was about to hit the frog with a wand. And the frog says, come on, I'm already a frog. So in any case, it was already bad here, and then you know what's happened in the last couple of weeks. So how would a conservative min-max strategy do during that period? Well, without showing that yet, here's what the SN of B curve looks like. Here's B 0, means invest all your money in the S&P 500 index. And here's B of 1, means keep all your money in cash. Notice 1, 1. You get your money back. And so the best long-only portfolio would have kept all your money in cash during that period. At least you'd have $1 back. If you put half in each and let it ride, you get this midpoint. It's too bad you didn't know ahead of time how those 13 months would have gone, or you would have lever-armed 6. You would have gone long 6 in cash and short 7 in S&P 500 index, and you would have achieved 2.3. Well, the universal portfolio actually applied strictly to that period would have given you a factor of 1.1. So you could have made money during that period. So I do want to caution you, this period, 13 months, if I'd picked another period like 3 months, you might get SN hat. In fact, most of the time you get an SN hat that's below 1, but it's above SN star, above what you could do with hindsight. Okay, now for some comparisons. In the general market, you have a known distribution, a portfolio strategy that maximizes the growth rate, and a growth rate of wealth. In a horse race market, in which the market vectors are the basis vectors for the positive orthant, all of a sudden you get Kelly gambling for the optimal investment, and you get an entropy rate for the growth rate of wealth. For wrong distribution and a penalty in growth rate, you now get a a penalty in a growth rate of wealth, which is a familiar quantity in information theory. It's called the relative entropy, or the Kullback-Leibler information number. And it turns out to be the mutual information in the special case of joint distribution. In the general market, you maximize the conditional expected log, and you get a growth rate of wealth. Here you get an entropy rate for the process, for the horse race market. The AEP specializes from a growth rate of wealth to the probability on a sequence. And then you get the universal portfolio theory on the general stock market. And if instead you had restricted yourself to a horse race market, which is essentially a data compression environment, you get the same cost of universality on both. And this constant that we came up with for the general market has been come up with by Starkov in the data compression environment. It's the same constant. So let me finish with this slide that summarizes what we've been saying, that growth optimal isn't simply just a disconnected goal, but one that is intimately connected to a number of other goals, some of them that seem unrelated. By definition, growth optimal is long-run optimal. But at competitive optimality, it's also short-run optimal. You have more money than your opponent with probability of half. It has a nice martingale property that brings in some new mathematics, and an asymptotic equipartition property that it has in common with physics and information theory. And a universal achievability, which has a counterpart in data compression. Then something completely unrelated, like black shoals, is seen to fit naturally into growth optimality. And then we find that if growth optimality is too conservative for you, for long-only portfolios, then you can achieve an amplification, and there's a theory associated with that, by going long and short. And finally, of course, throughout, there's a relationship with information theory. Thanks. Great. And optimal.